लाइव स्ट्रीम के लिए ऑन करते हैं। लाइव स्ट्रीमिंग के लिए ऑन करते हैं।
Good morning, everyone. A warm welcome to all the esteemed guests, faculty members, and research scholars here today. We are gathered here for a very special event organized by IIMT College of Management. The Institute is organizing a 5-day online faculty development program on entrepreneurial fund management, time series analysis, and time value of money. Today, it's a third session by the speaker, Dr. Sonia Anandhir, on the topic alternative methods of testing autocorrelation and heterostaticity of time series data. Let me welcome ma'am by giving her a brief review. It is our privilege to extend a warm welcome to Dr. Sonia Anandhir, Head of Department, PGDM, International Business,
Sakshi ma'am, you have gone on mute, please. Please unmute yourself.
Sorry for the instruction. Let me introduce our guest, Dr. Sonia Anandhir, Head of Department, PGDM International Business, James Rohini, as an esteemed speaker for today's faculty development program. With nearly 2 decades of corporate and academic experience, Dr. Dheer has made remarkable contribution to management, education, research, and training. Her expertise in international business, economics, and econometrics, coupled with her extensive work in the faculty and the managerial development program, makes her an invaluable resource for his session. We look forward to gain insightful knowledge from her vast experience and knowledge bucket. We welcome Dr. Dheer on the screen. Welcome, ma'am.
Thank you so much, ma'am. And I would like to thank IIMT Group of Institutions and the organizing team, as well as the Indian Economic Association, for having given me this opportunity today to share my knowledge in the area of econometrics and economics, along with my guide and mentor, Dr. Sri Prakash, who's also present here in the meeting today. I thank you all and I'm grateful for this opportunity. Shall we start the session?
Yes, ma'am.
Okay, I'd like to first of all share the presentation that I have prepared for the session and then I'll go ahead. I hope it is visible.
Yes.
Yes, ma'am, we can start the session. Your PPT is visible.
Okay. Today's topic is a very interesting and a very pertinent topic as a part of the science of econometrics. And the topic is about autocorrelation and heteroscedasticity. Before I really go on to explaining what these two terms really mean as far as time series data is concerned, it's important for us to understand what are errors in time series, because most of the discussion in the presentation today is going to revolve around this term called as error. So what are errors and where do they come from in time series and what is their significance is what we need to first of all understand. And then we will proceed to understand the concept of autocorrelation and heteroscedasticity. What are the various tests available to test autocorrelation and heteroscedasticity in time series data, and what are the remedies that we can use as researchers to deal with these problems if at all they arise in the time series that we are dealing with. So what are errors in time series? In regression and more specifically in time series analysis, errors, more specifically also known as residuals, represent the difference between the actual values and the predicted values of the dependent variable. And it is represented by the term ET, T meaning the time, E representing the error or the residual term. The difference between the observed value and the predicted value from the estimated regression model, which is calculated from the sample data that we researchers deal with, gives us the error term. So as you can see, the mathematical representation here, the residual ET is nothing but the difference between the observed minus the predicted or the estimated value of the observed terms. Where do errors come from in time series data? So in time series analysis, errors or residuals arise from several sources. First and foremost could be the model misspecification. The true relationship might not be linear between the two variables, but the researcher specifies a linear model or he uses a linear model, and that can lead to the generation of errors. Sometimes important predictors like some very significant important explanatory variables are not included in the regression models or the main model of the study. So if any explanatory variable is missing in the model, it leads to a systematic pattern in the errors and generation. Sometimes not included enough lagged values in autoregressive models. If a researcher is dealing with autoregressive models or distributed lag models, and they are not using enough lagged values in the autoregressive models that they are using, it might also lead to the generation of errors in the time series data being used. Simple example is that if one is forecasting inflation based on past inflation rates, but ignoring external factors like policy, specifically monetary policy intervention by the government during that time period for which the study is being conducted, the residuals may show a pattern rather than being random. Second significant source of errors could be external shocks and unexpected events. Macroeconomic shocks like recession and pandemics can cause large residuals to occur in time series data. Sometimes significant policy changes like interest rate hikes might introduce sudden changes that the model does not capture. And one very popular example which comes to my mind at this juncture is the 2007-8 financial crisis that took place. And if that period happens to be the period of study for the researcher and that sudden change or that change is not taken into account, that might result into errors and spurious results. Sometimes outliers are present in the time series data. These are the unusual observations that do not fit the general trend. They might result into errors. For example, a sales forecasting model might fail to predict the sudden drop in sales during COVID-19, leading to large residuals in that period. Now, it is always emphasized that the data should be random, or more specifically, errors should be random. There should be randomness in the errors. So why this is required? If a time series model is well specified, the errors should be uncorrelated. That is, they should not depict any autocorrelation. Second, they should have a constant variance. That means they should be homoscedastic and not heteroscedastic. Thirdly, they should be normally distributed, especially for the small samples. Obviously, for large sample cases, the central limit theorem holds, and as the sample becomes large, it tends towards normality. We, as academicians and researchers, already know this. However, the real world data often contain non-random residuals indicating underlying issues. Why should errors be random in regression analysis? In regression analysis, errors should be random to ensure the validity and reliability of the model's predictions. So if we want to ensure that whatever model we are using is valid and is reliable, we need to ensure that the errors are random in nature. If the errors are not random, the model may be biased, it may be inefficient, or may fail to capture the underlying patterns in the data. So here are 5 reasons why errors should be random. Number 1, to ensure the OLS assumptions. Now, ordinary least squares or OLS, generalized least squares or GLS, maximum likelihood, and indirect and multi-stage least square methods are popularly used for the estimation of parameters of regression equations. But the choice of estimation method depends upon the nature of data, objectives of the study, and assumptions that are associated with each of the above methods that I have just quoted. But OLS, or the ordinary least square method, is the most commonly used and popular method of estimation of the regression equations. And hence I emphasize here in this point that when I say that the errors in the time series data need to be random, it is because we want to ensure that our OLS assumptions hold. That means the ordinary least square regression is based on whatever assumptions they should hold. So these assumptions basically revolve around linearity. That is, the relationship between independent and dependent variables is linear. Secondly, independence of errors. That really means that there is no autocorrelation between the errors. Third, the errors are homoscedastic, that is, they have constant variance. Fourthly, errors exhibit normal trend, that is, they are normal in nature. They follow a normal distribution. When errors are random, these assumptions hold, making OLS estimators or ordinary least squares estimators in our regression models best linear unbiased estimators. The second reason why the errors need to be random is because we as researchers want to prevent biased estimates. If errors are not random, it indicates that some pattern or structure has not been captured by the model. So this leads to various kinds of bias, the most popular one being omitted variable bias. That means there is some missing predictor or an explanatory variable which is missing in our regression model. Second is model misspecification. If the errors are not random, our model may be misspecified. That is, the functional form may be incorrect. We are using a linear model, whereas the relationship might be non-linear between the variables. That is a common mistake one does, and that is called as model misspecification. Thirdly, it could lead to endogeneity issues. That is, if errors correlate with independent variables, our estimates become biased and inconsistent. So for example, if you're predicting sales based on advertisement spends, seasonality has to be taken into account. Errors may show a non-random seasonal pattern, making the model inaccurate. This is one of the most common examples that I can quote at this juncture. Thirdly, random errors ensure efficient estimation. If errors follow a pattern, OLS is no longer efficient. That is, the results might show large variances. And efficient estimators minimize uncertainty in estimates, ensuring better predictions. So if we want accurate or more accurate predictions, better predictions of our regression models that we are using, we would like them to be efficient. And for efficiency, we want to ensure that the errors are random in nature. Fourthly, it makes statistical inference reliable. When errors are random, standard errors are correctly estimated. That really means that our t-tests and f-tests remain valid, allowing for proper hypothesis testing. So you must be aware, whenever you are running a regression, the ANOVA table that you get gives you the f values. the mean sum of squares and the residual sum of squares, and hence the F value is obtained in the ANOVA table. And of course, once you are estimating the coefficients that you have obtained by running a regression equation, whether it is a bivariate or a multivariate regression, you get your t values and the p values. So you can only rely on these values once you ensure that your errors are random in nature. If errors are correlated or heteroscedastic, of course, your confidence intervals and p values become unreliable. So it is so much significant to us. So for example, if errors increase with income in a regression, predicting household spending, heteroscedasticity may lead to misleading p-values, and such results cannot be relied upon. And lastly, random errors improve predictive accuracy. If errors are random, future predictions are more reliable. If they follow a pattern, the model may extrapolate systematic mistakes, leading to poor forecasting. So for example, if predicting stock prices and errors are not random, the model may consistently overestimate or underestimate the future prices. So there is a problem of overestimation or underestimation that the researcher might face if the errors are not random, or they may show autocorrelation or heteroscedastic trends in them. So to conclude, I would like to emphasize that random errors indicate that the model is reliable for inference and forecasting. And if errors are not random, it suggests missing variables, incorrect functional forms, or other statistical issues that need to be addressed by the researcher. Now, two common problems associated with time series data, which I would like to deal with relating to errors in this presentation today, is autocorrelation and heteroscedasticity. The correlation between the random errors of a regression equation is defined as autocorrelation. The violation of this assumption makes the estimated parameters unreliable, and it is because the presence of significant autocorrelation also leads to the overall underestimation of errors, like I previously said. If the error is overestimated, then the significant coefficient may turn out to be non-significant. If, however, the error is underestimated, then the parameter which is truly not significant turns out to be significant. So it actually leads to type 1, type 2 errors in the hypothesis testing. And of course, the second assumption is that the exogenous variable is distributed independently of the errors of the estimation. In the case of multiple regression equations, it is further assumed that the exogenous variables are not related to each other, as well as not related to the errors of the estimation. The violation of this assumption may lead to the problem of heteroscedasticity in the data set. So these are the two major problems that we encounter as researchers while dealing with time series data. And once we are dealing with the errors or the residual terms in the time series data, understanding autocorrelation a bit more closely, autocorrelation is generally the malady of time series data modeling, whereas heteroscedasticity is more commonly seen in the cross-section data. One of the major difficulties with the use of least squares method with time series is the strong possibility that the errors are not independent. The correlation of successive terms in a time series is a lagged serial correlation if two time series are involved, that is. And it was shown initially, first and foremost, by Yule, how the distribution of two positively correlated time series tends to be a U-shaped curve, with the majority of the correlation tending towards +1. Also, further in case the errors of the time series of the variables are found to be autocorrelated, it was necessary to take care of the autocorrelation through an appropriate test till the coefficients are rendered non-significant. So far as the econometric modeling of time series is concerned, it is assumed that each observation of the series is an average. The validity of the time series modeling is based on the condition that the time series is stationary, and then there are separate tests to check stationarity of the time series data. Random walk model is one of the popular models used to test the stationarity of the time series data. Generally, one of the other following factors may account for significance of autocorrelation, like, as I already said, misspecification of the functional form of the estimated equation, omission of some decisive determinant of dependent variable in the equation, or choice of faulty or poor data sets. Now, the variance of least square estimates of the regression coefficients is very large if the errors are highly autocorrelated. If the autocorrelation could be reduced to a p-value which is less than 0.3, or more popularly when the p-value is less than 0.5, through a transformation of the series, then the variations tend to reduce and become closer to random errors. Two of the most popular tests used to test this thing, that is the test of autocorrelation, are the two tests by the name Durbin-Watson test and the Bruce-Godfrey test. However, autocorrelation can also be depicted through graphical representations. Now, the Bruce-Godfrey and Durbin-Watson diagnostic tests are often used to evaluate the significance of autocorrelation coefficient. But the Durbin-Watson test has gained more popularity than the other test of autocorrelation due to relative ease of its application. So I will be demonstrating Durbin-Watson test here today for your ease of understanding. Also, it being the most popular test to test autocorrelation, it made more sense for me to exhibit Durbin-Watson test here today. The Durbin-Watson statistic is represented by the symbol small d, as you can see here on the slide. It is also called as the D statistic, which is commonly used for testing the significance of the autocorrelation coefficient, which is rho. As you can see here, the rho, value of rho varies between -1 to +1. And accordingly, the value of D statistic ranges between 0 and 4. Now, once we have calculated our rows and the D value, we need to check for its significance. Now, there are two, for testing the significance of this particular coefficient, lower and upper critical values of D are referred to for accepting or rejecting the null hypothesis that the autocorrelation is significant or not significant in the time series. Now, the lower and upper critical values of D depend upon number of variables in the equation and the degrees of freedom. If the calculated value of D is greater than the upper critical value, then autocorrelation is inferred to be not significant. If the calculated D is less than the lower critical value of D, then the autocorrelation coefficient is inferred to be significant. If, however, the calculated value of D lies between the upper and the lower critical values, the autocorrelation test remains inconclusive. This is an important limitation for D statistics. This creates an ambiguity about this test. It was also suggested that the upper bound of D statistic, that is DU, and the lower bound of D statistic, DL, diverge more as the correlation between the errors increase and also as the number of observations decrease. Hence, one would obtain a smaller value of D when the null hypothesis is false. So, though the test is very popular amongst researchers, but there is an ambiguity involved with the application of this test, that in the sense that there is a region which gives us a non-conclusive region, which so the researcher can really not decide if the D value that is obtained happens to be between the value, the lower bound and the upper bound value. We can really not arrive at any decision whether to reject or accept the null hypothesis relating to autocorrelation. So, though popular, yet remains ambiguous in certain aspects. The Bruce-Godfrey test recommends the use of pth order autoregression models of the residuals. The procedure of calculation involves estimating the residuals of a bivariate regression function and then regressing the estimated residuals on original independent variable, which could be xt, and the lagged values of the estimated residuals. The length of the lag P is ambiguous as its value is not specified. Also, pattern of change in the value of the variable may differ between the variables. For example, again, I'm quoting this example from a research paper which was published long back, and it was written by Dr. Sri Prakash. So we thought it would be right to quote this example here today. So, for example, equity prices change several times even within a day. Prices of vegetables, fruits, and food grains change daily according to the size of market arrivals and stocking behavior of the intermediate traders. As against this, fixed prices change only in response to long-term changes in average cost of production. Consequently, fixed prices remain stable for quite some time, but the flex prices or the flexible prices change according to the state of demand in the market, while quantities offered for sale remain relatively fixed in short periods. Thus, this method may be difficult in empirical applications. So, every method has its own limitations, and they are also based on certain assumptions, which can pose challenges to the researchers if they are really looking for accurate tests for autocorrelation, problems like autocorrelation in time series data. Now, of course, Bruce-Godfrey test has obviously large sample size bias as chi-square. It is based on chi-square, the value of chi-square, and which is associated with large samples. Therefore, the test may not be appropriate for the evaluation of the significance of autocorrelation coefficient for small samples. That is one limitation of this test. Now, while we were working on a research paper, we tried to devise some alternative methods of testing autocorrelation, which were simpler in nature and better to understand. So, one of the alternative methods which we propose in our research while we were exploring the topic of autocorrelation and heteroscedasticity relating to time series analysis. So, one of the methods that we proposed in one of the research papers written by us was that if the calculated value, so we actually, for the first step in the method involves calculating the autocorrelation coefficient rho, which as you can see here on the screen is given by the formulas summation ui into uj divided by square root ui square into square root uj square. This is the formula for calculating rho for cross-section data. And in case of time series data, rho can be calculated as summation of the current value of the errors multiplied by the lagged value of the errors divided by the summation of square of lagged value of the errors. Once we have obtained our rho coefficient, we need to calculate the t statistics, which again is given by the formula rho multiplied by square root of n minus 2 divided by 1 minus rho whole square. If the calculated value of t obtained in this manner is greater than the critical value for the given degrees of freedom, the autocorrelation coefficient is inferred to be significant. If, however, the calculated value is less than the critical value for given degrees of freedom, then the autocorrelation coefficient is inferred to be not significant. Thus, there is no scope for the test to remain inconclusive, as in the case of Durbin-Watson test. There is an example which I can show you, which we applied on a time series data. So the model that we used was exports, India's exports being the dependent variable, inward FDI being one of the explanatory variables, and GDP being the other explanatory variable. So it was a multiple regression model that we used to test this method of testing autocorrelation in the data. And we also used logarithmic functions. So we use the log values of all the three variables used in this function. As you can see, the dependent variable is log value of exports, and the independent variables include the log value of inward FDI and the GDP. The first and foremost step involved estimating this function through OLS estimation procedure. And as you can see here, these are the values of our estimated coefficients T and F that we got here. Once we obtained these values, we applied the alternative test in terms of, first of all, obtaining the errors from this particular model. So once we have this model, it is very simple to calculate the errors as they can be calculated as the difference between the observed and the estimated values of the model. So once we had the errors, we also took their lagged values. Once we had the observed values of the estimated values of the errors and the lagged values of these estimated values, we calculated the rho coefficient. And once we had the rho coefficient, we calculated the t value. And in this case, the calculated value of t obtained is 1.931. Since the value of t is, we found the value of t to be less than the table value 2.02 for 21 degrees of freedom. Therefore, the null hypothesis was rejected that the residuals are independent of one another. And we inferred that there was a significant presence of autocorrelation in the function. In the second alternative method, we simply calculated the f value. As you can see here, that once we estimated our regression, the model function, we keep the model function as the same as function 1, which is shown here on the screen, where the dependent variable is the logarithmic value of the exports of India, and independent variables are the inward FDI and the GDP of India. Again, we took the log values of both these variables. Once we estimated this function, we calculated the errors. And once we had the errors, we regressed the current value of the errors so obtained on the lagged value of the errors. So that was step 1 of the procedure of method 2. And once we had this, we obtained the ANOVA table which gave us the f value. So we observed the f value, which is nothing but a ratio of the mean sum of squares of the regression and the sum of squares of the residuals. Now, if the f value so obtained is greater than the significance value or the table value of f, then the calculated f is taken to be significant, indicating the presence of autocorrelation between the error terms. It's a very simple procedure and very easy to understand. Here is the depiction of the same. Once we ran the regression on function 1, we estimated the errors. Once we had the errors, we took the lag values of the errors. We again ran the regression on the current value and the lag value of the errors. In the ANOVA table, we had the F statistic values. From table 2, as shown here, it can be observed that the calculated F is greater than the significance F. The null hypothesis being tested here is that the residuals are independent, and it can be inferred that the null hypothesis is rejected because the calculated value of F is greater than the significant value, and hence we conclude that the residuals are autocorrelated for the function taken for empirical analysis. So once we identify that there is a problem of autocorrelation in the data, what is the remedy for it? How do we ensure that we remove autocorrelation and that whatever predictions we are trying to make through our regression functions, they are accurate, and then that they are efficient, and that our model is valid? How do we ensure that? That means we need to treat our data for autocorrelation. We need to treat our function for autocorrelation. So one of the best ways to deal with autocorrelation is transforming the model. And before we go to transform the model, it is also important for us to really understand and investigate whether any important explanatory variable has been omitted from the function. And in case there is, we must add it and run the autocorrelation tests again to check if it was due to the omission of an important predictor variable or it is due to some other reason. If a predictor does not aid in reducing or eliminating autocorrelation of the error terms, then certain transformation of the variables can be performed. And one of the ways in which we can transform our function is like this. As a first step, I have taken a bivariate regression example here to make it very clear to you and to make it simpler for you to understand. In the first equation that you see here on the screen, it is a representation of the very basic simple regression model. Yt being the dependent variable, xt being the independent variable, b1 being the intercept term, b2 being the coefficient associated with our explanatory variable or the slope coefficient, ut being the error. This is how we generally represent our regression models, a two variable regression model. And once we have a two variable regression model and we have run the regression, we have our estimates, we also will get our error terms. So all you need to do is take a difference of the estimated and the observed values of the yt variables and you will get your error terms. Once you have your errors, again take the lagged value of the error and run the regression. So the second equation that you see on the screen here represents your second function that you will run. Ut is equal to rho ut minus 1 plus et, where the value of rho varies between -1 and 1. Once you have the rho coefficient from this equation, all you need to do is multiply this coefficient to the lagged values of both your dependent and independent variable. Once you do that and have obtained the results, you need to take the difference between the original dependent variable values and the independent variable values and subtract the values that you have obtained by multiplying the rho coefficient with the lagged values of the dependent and the independent variables. So once you have your equation 3 ready, rho yt minus 1 is equal to rho beta 1 plus rho beta 2 xt minus 1 plus rho ut minus 1. Once you have this, you need to subtract the values so obtained through your original observed values of yt and xt. And once you do that, you have your transformed function in the form of y star t is equal to b star 1, which is your transformed intercept, plus b star beta star 2 x star t plus et. So this is how you can obtain a transformed function with to get rid of autocorrelation. And if you've never done this before, if you've never run such kind of transformations for your regression functions, I suggest rather than applying it on a multivariate regression function, you should initially try it out on a bivariate regression function which is the most easy to understand and the most easy to execute also from a research point of view. So just take a simple bivariate regression model, estimate the autocorrelation, whether the errors are autocorrelated in it or not, just simply running the Durbin-Watson test or any one of the alternate tests that we have suggested here. Once you find that the function is having autocorrelation, the errors are autocorrelated, you can go ahead with transforming the model through this method. These are the 4 steps involved in the method. And you can go ahead with your estimations from this point onwards. Once you have understood the procedure, how to do this on a bivariate regression model, then you can maybe proceed towards multiple variate models. Coming over to heteroscedasticity, which is another very common problem seen in more seen in cross-section data, less seen in the time series data. But nonetheless, we will refer to this problem with respect to time series analysis here. The OLS method of estimation of regression equations also assumes that the exogenous variable is distributed independently of the errors of estimation. In the case of multiple regression equations, it is further assumed that the exogenous variables are not related to each other as well as not related to the errors of estimation. OLS method of estimation of regression equations also assumes that the error variances are homoscedastic, and each error is distributed with zero mean. The violation of this assumption is defined as heteroscedasticity. Several tests have been enunciated for testing the significance of the difference between error variances. If the error variances are heteroscedastic, then the reliability of the diagnostic test of regression and correlation coefficient is compromised. Therefore, it is necessary to examine the nature of error variances so obtained. Now, more popularly, there are 5 tests which are available to test for the presence of heteroscedasticity in data: the Bruce-Pagan test, Park test, Goldfield quant test, Gletzer test, and Spearman rank correlation test. In order to apply Park test of heteroscedasticity, the logarithmic value of error variances or errors is regressed on the independent variable. If the correlation coefficient or the regression coefficient attached to an exogenous variable is significant, error variances are inferred to be heteroscedastic. Park test is generally applicable to cases where original regression is specified in non-log linear terms. So it is therefore advisable to regress errors rather than error variances on the logarithmic values of the independent variable in this test. Similarly, rank correlation test suggests the calculation of rank correlation coefficient between the absolute values of the errors and exogenous variable. If Spearman rank correlation is found to be significant, error variances are inferred to be heteroscedastic. It is probable that the errors may be significantly related to one of the exogenous variables of the regression equation, while the error variances or the absolute errors are not significantly related to other exogenous variables of the system. If the second variable is picked up for applying either Park or rank correlation, test of heteroscedasticity will be erroneous, and the conclusion would be that the variances are homoscedastic. But Park and Spearman's rank correlation tests are relatively more popular among researchers. Goldfield quant test and Bruce-Pagan Godfrey tests, being more cumbersome in their procedures to test heteroscedasticity, are less popular. Now, most of these tests are complicated and take substantial time in calculating, and therefore, again, we propose 2 alternative methods of testing heteroscedasticity, which we have used in our research paper. The first alternative method focuses on the F statistic value. If the mean of all variances is taken, then it should equal each error variance. The equality of the ith and the jth error variances implies that the mean of all error variances of the regression model will equal each error variance individually. This is the assumption used in this test. The mean sum of squares of errors, that is the mean of the error variances, is given by the ratio summation the square of error terms divided by the number of error terms, which is represented by the symbol u square over here, where u square is the average of all observed error variances. This average is compared with the average of each error variance, and hence we obtain the F statistic. Whichever error variance is larger is put in the numerator. The calculated value of F may then be compared with the table value of F with the given degrees of freedom. So this is the first alternative method we have used to test heteroscedasticity in our research paper. And the second method, as you can see here, is given by the equation log u square is equal to beta 0 plus beta 1 log x1 beta 2 log x2. So what we are doing is now regressing the square of errors on the explanatory variables that are used in the original function, and we obtain the t value as shown in the given formula here. If the calculated value of T exceeds 1.96, the heteroscedasticity may be inferred to be significant. Well, again, one of the most popular ways of dealing with heteroscedasticity is transforming the variables by taking log functions of the variables, building separate models for different subgroups. But heteroscedasticity is a problem in statistical analysis that can be addressed by modifying the model or using robust methods for computing standard errors. So this is all from my side for the presentation today. If you want me to repeat any point again, I can do that. I can go back to those points. And if there are any questions at all, me and Dr. Sri Prakash are here in the presentation to address the queries.
Thank you so much for your session, ma'am. I would like all the participants, if there are any queries that you would like to ask, please step forward and ask. So I guess there are no questions for the session. And
Right.
so I would like to thank you, ma'am, for the session. And I would request everyone to please switch on their cameras for a group picture.
Thank you, everyone.
Thank you everyone for the participating here. But I would definitely not like to let Professor Shri Prakash sir to go without saying anything. So I would request him to kindly say something about the topic and address us so that we can also have a piece of knowledge from your side also, sir. So if it is okay with you, please, I would like to welcome you to say something.
Dr. Sri Prakash, please unmute yourself. Sir, we can't hear you. Please unmute yourself. Sir, is there any way that we can unmute from your end? Can we unmute him?
Ma'am, I'm checking if it is possible.
Hello,
Yes,
Yes,
sir.
sir,
may
Yes,
I
we
proceed to
can hear
say?
you. We can
May I
hear you.
proceed to say something?
yes,
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 you're free to
please.
say, sir. Yes, we welcome you to say something first. Please
Okay,
share.
thank you. First of all, I congratulate the organizers for selecting this very important topic of econometrics. Number two, I shall also like to congratulate Sonia for her brilliant presentation. But certain problems arise from this presentation itself. The basic emphasis of the presentation has been that the errors are random. So, in my opinion, the first task should be to test whether the errors are really random or not. there are few important methods of testing the randomness of the variables, whether it is errors or the other variables of the system. But the challenge, in my opinion, that arises from here, suppose we find that the errors are not random at all. What do we do? How can we make the errors random? How can we make the errors random? This is so I accept this challenge, and myself, along with Sonia Di, Dr. Rebecca, and other associates, we will proceed to take up this work of research in our future research projects. This is one thing that I would like to say. Second thing, why it is important to look at alternative methods of testing. Important point is that each method of estimation, irrespective of the variables that are under consideration, errors or otherwise, has its important assumptions, limitations, and strengths. So these limitations affect the precision of estimates. Therefore, it is always advisable not to depend upon one single method of applying the diagnostic tests. It will always be advisable to have a look at whether we are deriving conclusive results or not. This should be an important aspect of research investigations. Another thing which is important is why do this is the question which Sonia has also attempted to answer. Why do the errors arise? Time series comprises four components. Seasonal, every season has its own aspects, and the demand for particular goods and services get affected by the seasonal effect. Second component is business cycles. Third component is the consequence of the systematic factors that consistently affect the values of the dependent variable. This is known as trend. And fourth component is the residual. However, in case of annual time series, seasonal factor is averaged out, is eliminated. So the errors generally arise in time series data because of the influence of the business cycles. Sonia cited the example of 2008 worldwide economic slowdown, but business cycles are normally of duration of 3 years or at the most 5 to 7 years. So one way of moderating the errors that arise in the process of modeling time series data may be to convert the data by moving averages, 3 year moving averages that will take out a great deal of influence of the business cycles. So that will leave only two factors, systematic pattern or the trend and the residuals. The residuals will get reduced and certain problems may be, overcome by this procedure. Another alternative which one may resort to is to transform the data into logarithmic form. In log forms, the series is smoothened. So big deviations up and down, they are reduced in dimension and the errors also get restricted, constrained by this transformation. And there is no way that either of the two remedies can totally eliminate the residuals or the errors. Errors, by their very nature, are defined as the random errors or the errors of estimation. So, can it be possible to introduce the random factors? Random factors are random. We do not know what random factor is operating at a particular point of time until unless we know, oh, downturn is taking place, and so we can introduce dummy variable to take cognizance of that. But other random factors may not be observable, may not be quantifiable at all. So, an alternative way of overcoming this problem in time series modeling is to introduce residual itself as an independent variable in the original regression. I think I will have many things more to say in the next presentation tomorrow. But all the same, uh, important aspect of time series modeling is that of stationarity. And stationarity is something which is which requires that the economy replaces itself year after year without any substantial change. That is, the GDP of last year will continue this year also, next year also, next to next year also. So this is a highly stringent condition to be satisfied by the time series, because as the time itself is a variable, and along with time captures the influence of many variables, many factors which influence the dependent variable. So one method may be to introduce time as an additional variable in the system of equations. So these are, a couple of ways which have been tried and which can be tried with certain level of originality in the system of time series modeling. Let me here, for the beginners, because this is the very first session, I will like to say what are the systems of modeling time series data. One is autoregression model. That is, the lagged value itself is the determinant of the current value. But here, let me cite an example. Myself and Dr. Chitra Arora Bhatia, her thesis has been published by an international publisher. We examined the stock market data of 5 companies, daily prices, for a period of 5 years of the 5 companies. So you can assume that the stock market works 20 days a month. So 20 multiplied by 5 multiplied by 5, and for a period of 5 at 360, etc., etc. You can imagine the size of the huge size of the data that we analyzed. We introduced as many as 60 lagged values as the determinant of the current stock price. But we found, our finding is that, well, this has been a challenging problem in the modeling of time series data, to the determination of the length of the errors that should be included in the modeling. We found that introduction of more than one lagged value will introduce multicollinearity, which itself will, jeopardize the reliability of the estimates. And according to our findings, that not more than 2 or 3 lagged values should be included in any system of autoregression. Another aspect which has been emphasized in case of autoregression modeling has been emphasized by no less a person than Stewart and M.G. Kendall. they observe that econometrics is not a substitute of economic theory. The basic function of econometrics is to quantify the theoretical relation of economics and also determine their direction. So, statisticians have come out with this autoregression model, which is without any theoretical base. That is what invited this observation. So, all the same, certain things become fashion, like the dresses also are a part of fashion, they do change. And in academics also, there are fashion. Lots of people have followed this lead. But in my opinion, this is not auto-regression modeling of time series data is bereft of any theoretical base, and any econometric model which does not have any theoretical base is not acceptable. Another model is a much more powerful and much more interesting model. Sonia also emphasized is the distributed lag model. Then we have other, uh, models which comprise two equations or more than two equations, and different methods of estimations will arise. This will lead us to more advanced works or more advanced areas of econometrics. So I think I should not, uh, you know, load the listeners with heavier things which are, understandable at this stage. Thank you very much.
Thank you so much, sir. Thank you so much. And we are eagerly waiting for your solo session with us also, so that we can learn more. So we can say that this is a nice beginning to that, and we are hoping that that session will be much more enriching. And I would also like to thank Sonia ma'am for your time and such a nice session, and for
You
all the
have left
speakers
us
who
with a
have
bigger
joined us.
challenge. You have left us with a bigger challenge.
Oh,
More
expectations are more,
research
sir.
work has been left.
Yes.
Thank you. All the
And
same. Thank you. Please go.
thank you, sir.
Go ahead.
And for all the honorable participants here, I would request you all to please fill up the feedback and join us again at 2:30 p.m. for the next session. The meet will be open from 2:15, so everyone will be have chance to check their systems, and if issues are there, kindly contact us. And we hope to see you all again at 2:30 p.m. So with this, I would like to end this session, and I would again like to thank Sonia ma'am for your time and such a nice session, and Dr. Sriprakash sir.
Thank you, ma'am. Thank you,
Thank you
sir.
so much.
And the participants, if you are unable to join on Zoom, then you can join the YouTube live also.